we represent it in a more familiar way here. Basically, the pump pulse excites the system, and then two interactions excite the system, and then the probe pulse causes the emission of the field. There is another contribution from ground state bleaching, which is the probe pulse is scattered by the ground state hole. There's no electron there. And there is excited state absorption. If now the system is not 2-level, but is a 3-level or more level system, then maybe the probe can also be absorbed, driving the system to a higher energy, and then that will be excited state absorption. So the most basic transient absorption signals. And they, of course, can be resolved in spectrally. So that is, if we then spectrally resolve the probe pulse, we have a transient absorption spectrum. This is one-dimensional spectrum. Okay? Okay, so we can do transient absorption like this. We have a laser beam splitter, and then we can do some frequency conversion to have a pump and probe pulses with the desired wavelengths, and then we have to focus them on the sample somewhere here, and we delay one of them, either the pump or the probe, doesn't really matter. And we also have to modulate the pump so that we can do the difference with pump and minus pump. And what is important is that the pump beam goes to the block, goes nowhere, and the probe beam goes to the spectrometer, where we will use a diffraction grating to spatially disperse it and get the frequency information simultaneously for every laser pulse. So this is one-dimensional pump probe spectroscopy. Now, what if we want to specifically excite different energy levels in our system? Then we have to do two-dimensional spectroscopy. That means we want to not only resolve the probe beam as a frequency, but also the initial excitation, that is the pump. And one way to do this, and that's a real way and has been done a lot, this is the double resonance experiment, where we use narrowband pump. So we tune the frequency of the pump to match the different states in our system, and then we perform transient absorption. Then we can stack these experiments to make something like a quasi two-dimensional spectrum. This is very useful, but it has a few problems. One is that it's quite laborious to do transient absorption experiments under the exact same conditions, just varying the excitation wavelength. It's also time-consuming. And that is one story, but another more critical issue is that we have the transform limit, right? The transform limit. What is the transform limit? You surely talked about. It's the principal thing in any ultrafast spectroscopy. Normally, the pulses that we use, if we have nice pulses, they look something like that. No more colors. They look something like that, right, in the electric field. And the envelope is something like that. Oh, this is also forward bond. Yeah? Okay. And then let's check here. Then the envelope of that is a Gaussian. Now, I forgot to mention, this is in time. Now in frequency, we Fourier transform a Gaussian, it's, what is it? Yes, but the width, here we have, the transform limit is that the again, it's also like the uncertainty principle. The product of the two widths in time and in frequency domain is 1. This is not the Heisenberg uncertainty principle because there's no Planck constant there. It is simply mathematical Fourier transform limit. So we have, what I'm trying to say, we have narrow band pulses, it means they are broad in time, right? So we lose time resolution. Or if we have broad pulses, then we cannot make them narrow in frequency. So if we want to measure very fast processes, we cannot do that simply. Okay, what can we do then is a Fourier transform spectroscopy. And you know FTIR or NMR, it's Fourier transform spectroscopy. The concept is exactly the same. We measure the signal in time domain or in space domain if you want, and then Fourier transform it to get the frequency domain in inverse seconds or inverse centimeters. So how does that work here? Basically, even in pump probe, what we do is we spatially disperse the probe pulse onto the diffraction grating. That is Fourier transform. That is, let's call it analog Fourier transform. We can also do it digitally. If we measure the response in time, the emitted field, and then we can do it numerically. The only problem is we need to have very fast, these are very fast oscillations on femtosecond or sub-femtosecond scale. Anyhow, in two-dimensional spectroscopy, we also Fourier transform the signal with respect to the pump, and then we get the two frequencies. Now, otherwise it's the same thing. We have in pump probe, as I said, we have two interactions with the pump, and so the only difference in order to get the frequency information is that we should not give the two pump pulses at once, but we should vary them in time so that we can do the Fourier transform. So then, if we go back to the, so let's just, before I close it, look again at this diagram. We have two pump pulses that they are separated by some time, which we sweep or scan. We usually, from NMR nomenclature, we call it tau or T1, and this is called coherence time. So what happens is that the first interaction, it sends the sample in coherence, right? And coherence means it will oscillate with the frequency of the transition over time. It will dephase eventually, but before it completely dephase, we can send the other pump pulse, which will, for example, send the system to the excited state. Then we have our usual delay between the pump and the probe, and then the usual probe, and then we measure the signal. So this can be done also in analog way. That means to send the pump to a diffraction grating, but then we again have the Fourier transform limit. What usually we do is this we do numerically by Fourier transform of the signal. Okay, so just to give the analogy, make it even more robust, I will repeat one of the diagrams. Let's even do the same. I should not have deleted it, but we start with the ground state. I will use, and we have again our, now it is K1, our first pump, and then we have some coherence. Then we have another pump, let's say K2, that will create population in this state. in this, then we have some waiting time, and then we have the probe pulse, let's say here, and then we have again coherence, and then the signal is detected. It's the same thing. The only difference is that here we have different wave vectors or different time ordering of the two pulses. So we can control that. And then if we can control that, we can also control which pathways we detect. For example, we can draw another pathway, almost the same. Let's say up to now is here, 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 up to now is the same, and then the probe field can come like this. Oh, this doesn't work. Sorry, I made a... This is unconventional way to draw it. The conventional way to draw the same way is just inverted, because there is a... The convention is that the last is always on the left side, the emission. It's just convention. So then I will just invert it. So we have the first pathway here, and then the first interaction here on this side of the density matrix. Then that will be the second, K2. And then we have population. And then we will do the probe, that's the K3 in our case, and finally is the signal. So this is almost the same, except it is not. This is called rephasing pathway. This is called non-rephasing pathway. The reason is because here we have a coherence on one side and coherence on the other side. The difference between the bra and the cat is the sign of, basically the frequency is positive or negative, if you wish, of the oscillation. Which means that any kind of phasing or dephasing that is accumulated here will be reversed in the other period. So we have positive frequency oscillation moving in one direction, then negative frequency oscillation moves it back in the same direction, and that means if there is some dephasing here, it can cause back rephasing in the second period. So this is what is called also a photon echo, because what happens is that you have different molecules, right? They slightly oscillate, they oscillate with slightly different frequency. Over time, this will destructively interfere, and what you observe is dephasing. But then in the next period, the frequency is opposite, and so in the next period, they will come back to their coherent state. So that's called rephasing. Never mind. The issue here is that we can control which of these types of pathways to measure, because here the wave vector is plus, here is minus, here is plus. If it goes right, it's plus. If it goes left, it's minus. And then the signal is emitted. This one is emitted in K1 minus K2 plus K3. So if we just sum the vectors, we know where the signal is coming. And this signal is coming into minus K1 plus K2 plus K3. It's going in a different direction. So it's physically, the echo signal is going in a different direction if the two beams are not collinear. And so we can choose where to put the detector, either to measure one or another pathway. This is one of the, and they tell us different things about the system. Oh, come on. Okay. in the end, we Fourier transform, and we get the frequency map that I showed you before. Now, this is interpreted as a joint probability. That means a signal at some position here, let's say this peak here. That means frequency omega A, which corresponds to that state, on one side, and omega B on the other, on the detection axis. How we interpret that? This is the probability to find a system in state B. So basically the population of state B after initially we excited the system in state A. Alright? So this cross peak is the probability that the system is here if it was initially here. Alright? Or let's say this cross peak, just the same thing. This is the probability to have population of this state, C, if the initial state was B. So you see, the cross peak gives us the couplings between different states. And this probability changes over time, right? Because there is dynamics in the system. There are these rate constants of relaxation or energy transfer or whatever. So over time, the populations will change, and as the populations of these states change, the intensities of those peaks will change. So from the time dependence of the cross peak population, we can get the energy transfer. And also, if we have delocalized states, like let's say these two states are delocalized, then you remember we have the monomer states, because of their interaction, the energy splits. We have these excitonic states, and both molecules A and B contribute to the excitation. Then it means we probe one, we can detect the other, or we probe the other, we detect the first one. We have these cross peaks, even at time 0, before any energy transfer. So the 2D spectrum can tell us about delocalization or excitonic coupling, and it can tell us about energy transfer. Like I said, here we have energy transfer from A and B. We'll have the cross peak at 1. This is omega tau, is the Fourier transform of the coherence time, and omega t is the detection frequency. And like I said, this is dynamic, it's time dependent, so the cross peaks will change in time. And if we follow, let's say this cross peak here is that, it will rise as the energy goes from one state to another, and then it may decay back as the system goes to the ground state, for example. And in a realistic system, you have everything together. You may have excitonic states, and these you can see at very early times or 0 time as cross peaks. And as you go later with the waiting time, the time between the pump and the probe, then you can get energy transfer cross peaks. All right. And also you can separate downhill and uphill. Now, if you have energy transfer, you have what's called the detailed balance. From the Boltzmann distribution, there must be a relationship between the ratio of the forward and backward rate constants and the temperature. If you have enough vibrational energy, thermal energy, even if that state is lower in energy, the system can go back to the higher energy state. And you can quantify that simply because you will have this downhill energy transfer peak, you will also have an uphill energy transfer peak. Their amplitude ratio, their intensity ratio is your equilibrium, is your the ratio of the rate constants. Okay? So you can, in a way, simultaneously view the energy transfer in one and in the other direction, which you cannot do in one dimension. Now, another thing is that the two-dimensional line shapes can separate, like I said in the beginning, the homogeneous from inhomogeneous broadening. Now remember, in the homogeneous broadening, it affects all the molecules equally. So let's say we have a homogeneously broadened system. The two-dimensional equivalent of that is the two-dimensional Lorentzian, this diamond-shaped spectrum. In this more for infrared spectroscopy, it's not so nice in the electronic, but in principle it's the same. So it doesn't matter, a homogeneously broadened band is wide along the diagonal as equally wide across the diagonal. Now, in the other limit, in the inhomogeneous broadening, what we have is we have many different molecules with many different energies. And then, if we excite that, let's say this is the lower energy side of the spectrum, we excite that, we probe that, we excite the higher energy one, we excite that, we probe that, so we have a correlation. Yeah? We have a correlation, each of them, if that is completely static, inhomogeneous, then the spectrum is simply a diagonal line. And the width across the diagonal is the homogeneous width. The width of each individual bands. So now, what is like, we do an ensemble measurement, but we can get information about the heterogeneity inside the ensemble. Now, these are two limits, right, as I said. In reality, we have something in between, first of all, so we can quantify that. But also, this is not static, it's dynamic, because the energy fluctuates over time. And in fact, we can follow that. This is called spectral diffusion. Let's say we take this one here, it will, the low energy side, it will not stay there forever. Depends on, it may or may not. If it fluctuates over time, that means it moves along the frequency. Then what we will observe is that the initially inhomogeneous band starts to diffuse and becomes more uncorrelated or more circular. And this is the spectral diffusion. We can quantify that. There are several ways. We can quantify that by the ellipticity. That means the diagonal width and the difference of the diagonal and the anti-diagonal width. As time goes, if there is spectral diffusion, the ellipticity will be lost. There are other ways to do it, central line slope, nodal line analysis, and so on. We don't have to talk about that, but it is a very commonly used way application of two-dimensional spectroscopy, because it tells you about the solvation, the solvent relaxation of the molecules, the motions of the molecules, and so on. And finally, I said the 2D spectroscopy tells you about coherent dynamics. Now, if you can have coherence between exciton states, for example. That means you excite coherently two exciton states, and then the system will move, constantly oscillate between these two. And if you follow the two-dimensional spectrum, you will see that one cross peak disappears, the other one appears, and then they just exchange. So you can follow that in time and follow the oscillations in the cross peaks, especially if you measure the rephasing diagrams. So this is basically the main things that we can learn from two-dimensional spectroscopy, and maybe we can make a short pause. Then I just show you a few examples of setups and spectra, but the this is the main part to understand the technique. So maybe it's time for a question now, or 2 or 10, if you have. Yes.
About this Feynman diagrams.
Yes.
This wave vector is one
Yes.
is plus and the other is minus. It's simply the directions or not.
Yeah. So there are 2 things. One is simply the directions. You add one vector, or depending on this k. In this case, what I mean by k is just the wave vector. So simply the direction of the propagation of the beam. And now you take this vector and you sum it with the other one. Let's say you have the 2 non-collinear vectors, and then you can find the signal. But I mean the 3 vectors, not the 2. K1, K2, and K3. And actually, you will see, there is another, this you will see just in a second. There is another thing that there is also plus and minus frequency. In one case, the right hand arrow will add frequency, the other one will remove frequency, positive and negative frequency. So you can, from the diagram, you can also tell what the frequency of the emitted radiation will be. But eventually this you will translate into proper formulation of in terms of quantum mechanical expressions and quantum electrodynamical expressions, where you propagate the density matrix and multiply with the laser field, integrate and get the proper formulation of the outgoing radiation. Never learned it. I do it very rarely. Okay. Other questions? Yes? Okay, I show you just a few technical examples. There are many ways to do two-dimensional spectroscopy, many possibilities and combinations in between. Basically, it boils down to 2 most common setups and variations in between. The non-collinear and collinear geometry. The non-collinear, or also called boxcars, is where you have all the, or fully non-collinear, all the 3 pumps are, all the 3 laser pulses are non-collinear, coming from different directions and different incident angles on the sample. And then what you have is that the signal is emitted, like I said, you can find where the signal will be emitted by summing properly the wave vectors, and then you can put a hole in the mask and block all other beams and put the detector here. Okay. And if you want to measure another signal, you can put another hole, or you can simply switch the time between the 2 pulses. It's equivalent. Anyhow, what is necessary in this case is to use another 4th beam, what is called local oscillator. This is because the signal must be heterodyne detected. That means you cannot just detect the incoming field and then Fourier transform, because you need phase information, and our detectors do not record phase. In order to keep the phase information, you basically have a reference pulse and you measure the interference between your signal and the reference pulse so that the phase information is still there. This is called heterodyne detection. never mind. The important thing is that you need a reference local oscillator. It also acts to amplify the signal in a way. So this is the non-collinear geometry, and it has this. It's very flexible because you can separately measure the rephasing and non-rephasing diagrams. You can change the polarizations of all the pulses, so you can really control what optical responses you want to measure. But it's very tricky and very difficult, and actually in the visible, it's to date, every experiment has some kind of artifacts, because in order to get the proper absorption, transient absorption, two-dimensional absorptive signal, you have to measure the rephasing diagram, but then you have to measure the non-rephasing, and then you have to sum them up properly without any phasing artifacts, and that's not really 100% achievable. Now the other way is to do pump probe geometry. That is a much simpler way to do two-dimensional spectroscopy. Basically, you have the difference is the two first interactions are collinear, so it is simply like the pump probe, normal transient absorption, except that you have a delay between the two pulses. But then, then is the question, how do you get the signal, the two-dimensional echo signal, and not the pump probe? Because the pump probe signal will also be here. And also the probe signal itself, the probe field itself. So you have to isolate the signal from the background, and that is done by phase cycling. I will tell you about it. Here. So in the first case, in the non-collinear, I more or less, I think you understood how we collect the signal. We have the phase matching condition, and we just choose the detector to be in the phase matching direction. And then we can choose either the phasing or non-phasing. In the phase cycling way to select the signal, that is what we use with the pump probe geometry. We have to, it's kind of equivalent, the phase and the wave vector. We can select the signals by their phase dependency. So what is here drawn is just the echo signal before Fourier transform. So over the first coherence time, tau. This should be tau here in the other. So this is the coherent oscillations, and then they dephase over time. Now if we flip the phase between the first and the second pulse, then the oscillation also flips. Because what happens is that the first pulse creates a coherence, and then the second pulse can either constructively or destructively interfere with that. So it will flip the phase of the oscillations. And then we can take the difference of that. It will only keep the oscillatory signal, and every background which does not oscillate will be subtracted, right? So this is phase cycling. Okay. Now, what do we need to do as an optical setup? Is just very briefly, I cannot show you now this in reality, so there is not much point, but there are, as I said, many ways to do. The first ever experiment was done with an interferometer constructed like this. Basically, you have a laser beam, and then you have beam splitters to split the laser beam in 4 different beams, and then you put optical delays on each branch, and then you need a tracer to calibrate you need attosecond stability of the delays, actually sub-attosecond even if you, depending on the frequencies that you want for UV, you need very, very high stability. And all the beams are then focused on the sample, and then you have the mask that I showed you about, then the signal of interest goes to the detector. Here at the lens you can see different spots, the first beam, second beam, probe beam, and then the signal. Now this is very complicated to align and maintain, so people don't do that much. Nowadays most setups have diffractive optics, that is a piece of glass that will split the incoming laser beam into several identical beams. And so you have a diffractive optics to split the beam, and then you have to control the delay, and usually the delay is not controlled with a classical retroreflector, but you put a pair of wedges, so basically you use a refractive index of the glass, or whatever, fused silica, to retard the beam, and by moving the wedge you can increase the material and delay the beam. But at the end it's the same. You have the four beams. One is a local oscillator, and on a curved mirror which will focus them onto the sample, and then you have a mask to isolate the signal that you need, and then you have a spectrometer. So that is the fully non-collinear setup. Then you have the pump probe geometry setup. What you have is that you have already existing transient absorption setup. You have a laser, you have some kind of frequency conversion, just no regular pump probe, and then what you can do is put a pulse shaper, which is a device that can split the pulse into two, and control the delay between the two pulses, and also control the phase, so because you need to do phase cycling. And then it's the regular pump probe story. Now, what is a pulse shaper? There are various ways to do pulse shaping. One is you simply do Fourier transform, then shape it in frequency domain, and then inverse Fourier transform, and then you have shaped pulse in time domain. So this is analog Fourier transform. You have the input pulse. Analog Fourier transform means you spread it, disperse it with a grating, and then you have a mask that will separate different frequencies. Basically, to make the split, you need to have some kind of fringe pattern, and then in the mask, and then when you recombine that with the second grating, you have a strain of pulses. That's a pulse shaper. But there are devices that you can buy that can do that a little differently. With, for example, this is the acousto-optic programmable dispersive filter. What you need to know is this is a nonlinear crystal with the birefringence controlled by a radio wave, and then it's just there is a cable to the computer, and you dial the shaping that you want, and then you want 1 pulse, 2 pulse, 3 pulses, and that's what comes out. There are hybrid ways that you can use a pulse shaper to split the pump, and you can use diffractive optics to separate the signal from the background to have kind of best of both worlds. There are other ways. There is this called translating wedge interferometer that can also, it looks like that. These are again wedges. It will create two identical pulses. It's called also twins. The problem with this is very, very inexpensive and very, you can just buy it. But you cannot control the phase with that, so you need another trickery to control the phase. So these are the examples of setups around the world that exist nowadays. Now I'll just show you some spectra from photosynthesis. Now, when I say photosynthesis, we are focused on the photosynthetic pigment protein complexes, like in plants. This is the photosystem 2 and photosystem 1. They contain chlorophyll. And chlorophyll is the green pigment that absorbs the light and does also the pigment that does the charge separation to extract electrons from water and then move them towards carbon dioxide, right? So the primary charge separation is between two chlorophylls. But most of the chlorophylls in the photosynthesis are in the what is called light harvesting antenna. So this is the photosystem 2 supercomplex. Supercomplex means it made of many different subunits. This is light harvesting complex 2. This is a trimeric subunit here. There is also a light harvesting complex. This is called the core complex. And here in the middle is the reaction center where the charge separation occurs. So these are all chlorophylls. The blue here is chlorophyll B, and the green blurry thing is chlorophyll A. There are also some other pigments, carotenoids. So this is all altogether around 200 pigments. This is when we look from the top. This complex lies in the membrane here, right? And when we look from the top, it looks like that. When we look from the membrane, it looks like that. Here is the oxygen evolving complex, splits water, and the electrons go on the other side of the membrane. And this is the entire surface of the complex, and here are the chlorophylls. So in order for this to work, all these chlorophylls, they absorb the energy and they must transfer it to the reaction center, and very fast before it goes back to the ground state. So the efficiency of the charge separation will depend on the ability of all these chlorophylls to move from anywhere the energy to the reaction center without any losses. And